All right, so welcome to Math 383 Complex Analysis. This is lecture 2. And what I want to do today is I want to talk about experimental mathematics. So I want to talk about formulas for derivatives, product rules, the Cauchy-Riemann equations, Green's theorem. We'll see how far we can get today. This is supposed to be a graduate level class. What this means is you are supposed to be at the point in your mathematical careers where you can actually learn a lot of the material on your own by reading it from a book or by working with other people in the class and reading it together. When I was in grad school, we formed study groups for all the classes we did, for seminar series and whatnot. This is how we typically learn subjects. I will go over a lot of things in class, but I'm not going to be able to go over everything in the book. There's just not enough time to do that and move at a graduate pace. And when you are applying to graduate schools, I will be able to put in letters of recommendation. We moved at a graduate pace. Even though it's a 383 class, this is a graduate level class. What I want to do is I want to try to have the lectures be value added. So if there's a standard proof in the book, I'm not going to do the standard proof in class. I want to try to talk about perspectives and ways to think about it. When I was at Princeton as a graduate student, the joke was, why would we have a class if there's a good book on it? When I was an undergraduate, my professors who went to Princeton said that when they were students, the joke was, why have a class when there's a book on it? So it mellowed out a little bit in the intervening years. And the philosophy was to throw you into research quickly. How do you do research? That's the goal at the end of the day. The goal is not to just keep reading things that have already been done and regurgitate on problems. It's to come up with original stuff. So a lot of it is trying to figure out, what should you try to prove? What should you conjecture? And so what I want to do is I want to talk a little bit about that through stuff you've through stuff you've seen in Cap 1 and 2 and 3. And use that as a starting point, and then we'll transition from that into complex analysis. Okay, so the first is the definition of the derivative in one variable. And so there are 3 different ways of writing the definition of the derivative. And so the standard one is, f prime of x is the limit as h goes to 0 of f of x plus h minus f of x over h. And if we think about what's going on, if I take, some point here is x, and here's x plus h, we're approximating how much the function has changed in that small amount of time. I'll explain this later. And so we have the average rate of change in that interval of time. And then in the limit, as that interval of time gets smaller and smaller and smaller, the average rate of change converges to the instantaneous rate of change. So has everybody seen this definition of the derivative? There's another version which is so similar to this, it's barely worth mentioning. F prime of a is the limit as x goes to a of f of x minus f of a over x minus a. Have people seen this as the definition of the derivative at a? How can you show that these two are the same? Yes.
These are sort of the same processes that you can.
Okay.
Actually, never mind.
Okay.
You can change variables, you just like h equals x minus a.
Yeah. Just try x equals a plus h. So h going to 0 is the same as x going to 0. So h going to 0, same as x goes to a. There's really no difference between the two. There's another definition of the derivative. F prime of a is the limit as x goes to a of f of x minus f of a minus f prime of a. Oh, let me see. I'm going to do it this way. Times x minus a over x minus a equals 0 means the derivative of f at x, at a is f prime of a. How many people have seen this as the definition of the derivative? Not as many. So this is something you should have seen. this is a little bit more work to show that this is the same. But if you think about what's going on, okay, I've got f prime of a times x minus a over x minus a. This is screaming at you, we'll just cancel the x minus a's. This is f prime of a. So if this limit is 0, I pull this out, and I get basically, oh, okay, that's the same as the second definition, is just f prime of a. Why is this a good definition? What this is saying is the value of the derivative at a is that unique number, such that if we try to approximate where are we at time x, well, we're where we started, times our instantaneous speed, times the amount of time elapsed, that this is such a good approximation that even when we divide by the amount of time, it's still going to be very small. That this is so good that this is going to go to 0, that our error is going to be much smaller than x minus a. Yes? Correct. Sorry about that, dealing with something with my family. Just gotta quickly confirm something, nothing from the doctor. Okay, so if you look at what's going on, it's supposed to be so good that even when we subtract, or even when we divide by the amount of time we've moved, there's essentially no difference. Imagine at time 0, I'm 5 miles from home. Where would you estimate I am a billionth of a second later?
5 miles.
Yeah, and if you just look at the difference, it's going to be small, right? So if I just want the numerator to be small, I can put basically anything I want over here. And as long as my function is just nice and continuous, it's going to be small. So having a small error in the numerator is not impressive. You know, if I move 1 billionth of a second, I just say I'm where I was. What I want to do is I want to look at how much am I off by relative to that small amount of motion. That's why this is a really good definition. And this is the definition that generalizes for multivariable calculus. Okay. So if I want to do something in several variables, the definition of the derivative is not that all the partial derivatives exist. So we would say, you know, df dxk at the point A is the limit as h goes to 0 of f of, do it this way, a plus h ek minus f of a over h. And ek is unit vector 0, 0, 1, 0, 0. Hopefully that's clear. It's got a 1 in the kth spot. So E1 is just moving along the x-axis, and E2 moving along the y-axis, and so on and so on. But the way we calculate partial derivatives is keep all the other variables the same and change just the one you care about by a little bit. So it takes less than a minute to learn how to take partial derivatives once you know how to do derivatives. Just imagine all the other variables are constant. Now, if we want to know what it means by differentiable, we say f is differentiable if the limit as the h vector goes to the 0 vector, I'll do f of a, I'm sorry, f of x minus f of a minus grad f at a, x minus a, divided by x minus a equals 0, where the gradient of f at a is, you know, df dx1 at a dot 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 df dxn at a. Again, all these notes should be available online. There is a mistake in what I have written. So who can detect the mistake?
I have a question. I don't know if it's a mistake.
Okay.
You're talking about, but like this is vectors. So I'm just wondering, is that product like a dot product or?
So this would be a dot product here, yes. So that would be a dot product here. So that's one mistake. Yes.
Wouldn't limit is h equal to 0?
Oh,
Need it-
sorry.
it would just x equal to 0.
Yeah, it should be x approaches a. That is a mistake. That's not the mistake I meant to do, but that is definitely a mistake. There's one more mistake. Yes.
Divide with vector by vector.
What do you mean I can't?
Like, you have to be more.
We've only had one class. Well, one class and change. You don't know what I can do yet. You don't know my capabilities.
Take an absolute.
Sure. Absolute value, absolutely. Then we now have something else. We cannot just divide by. So you have to be careful when you extend from one dimension to several dimensions. We cannot divide by vectors, but we can divide by the amount we've traveled. And so when we're trying to calculate what is the derivative, what's going on is we're basically saying where we are is equal to where we were plus a velocity vector times how much we've traveled, the time traveled, the time elapsed. This is the great notion of what it means for a function to be differentiable. It is not enough for all the partial derivatives to exist. So as a nice find f of xy such that df dx and df dy exist at 0, 0, but f is not differentiable. So I can give you a function where the partial derivatives exist, but the function is not differentiable. If you think about it, the partial derivatives existing is giving you very little information. It's saying, if I approach along the x-axis, if I approach along the y-axis, we know everything is fine. Well, this is the nice thing about doing lectures like this. I should be able to just bring back to, yes, to lectures from earlier. And you have to imagine the scribble of the preschool kids, where we have some god-awful path converging to the origin. We have to be able to travel along a path like that. In one dimension, there's really not that many paths to look at. It's not a big deal to have a limit. But in several variables, it is a much more intense statement. Yes?
So the way that I've seen this definition before, the df is more like a linear transformation, not a vector. I guess, is this somehow the same thing?
It's basically the same. I mean, because when you do this dot product over here, you're going to get something that's linear in all the changes.
Okay.
It's just how I'm choosing to write down the linear transformation.
Okay. Which is just the transpose or something like that?
Right. So if you want to do it as vectors, you would do it the transpose of this times that, or putting the dot product is the same as doing the transpose.
Okay,
yes. So one of the joys is there are so many different notations one can use. I was mentioning in 349 earlier today that I learned spherical coordinates from the physics department before I learned it from the math department. So I instinctively want to use a different choice of angles than we use in math departments. And so whenever I teach multivariable calculus, I have to constantly be on alert to make sure my theta and my phi align with the math department and not the physics department. So you do want to be aware of the notations. All right, so quick calculus test to see what everybody's level. Oh, yes?
But I asked about the last one. So I wonder why is.
Oops. Or does the denominator have what? Oh, because the numerator is a number, right? This is a function which gives me a real number as a function of a vector. And so you could have double lines as well. And this is a good notational issue as to what do we want the double lines to mean. Some people don't do double lines for vectors. They just use single lines and absolute value for vectors as well. Say, look, let's just extend the notion of absolute value. The absolute value of a number is what you would expect it to be, but for a vector, we're going to generalize it using Pythagoras. And it's going to be the square root of the sum of the squares. Or if it's complex numbers, you would use the complex conjugate transposes.
Thus the zero should not be a vector.
I'm sorry?
Thus the
Oh, yes. That was the other error I had. Thank you. That should be 0 the number, not 0 the vector. Thank you. So it's very easy to make mistakes as to which things are. And this is why I wanted to do this, to really emphasize the numerator and the denominator are very different quantities. But once we take the length of this, now we have a real number divided by a real number. When we looked at what was going on before, we could have actually put in an absolute value, right? But you would never put an absolute value if it's just tending to 0. There's no need. If there's time at the end of today, I'll show you some identities from Pascal's triangle where we should really put in some additional combinatorial items. But since the items are 1, well, we're not going to really explicitly write multiply by 1. It's a waste of time. But in terms of trying to understand what's going on, it's often useful to have that. Who are my physicists or potential physicists? Have you looked at rationalized MKS? So they set the speed of light to be 1. They set the gravitational constant to be 1. And by doing all of this, they clean up a lot of the equations. And it also is now at the point where when I look at it, I have absolutely no idea what I'm looking at. When I see G, when I see C, I have some idea of what system I'm looking at. And sometimes when you clean things up too much, okay. So let's test and see how people's calculus is. I've got 3 questions, x cubed, x to the square root of 2. Can somebody tell me the derivative of the first? 3x squared, that is correct. The second one. Good, and the third? Excellent. So how did you calculate the derivative of f of x is 3x squared? Okay, so you're using the rule, the derivative of x to the r is r x to the r minus 1. But we need to prove that. So how do you prove the derivative of x cubed is 3x squared? What's the key input?
It's like some binomial theorem, and you can use whatever exponent you want.
So I can do, x plus h cubed is x cubed plus 3 x squared h plus 3 h, x h squared plus h cubed. And then you just argue and you just use the definition of the derivative. Okay, how do I calculate the derivative of x to the 3 halves? Is 3 halves x to the minus x to the 1 half? Yes. Okay, but now I would need to know, how do I calculate the Taylor series of x to the 1 half, which would require me to differentiate. How do we take the derivative of x to the 1 half? So that can be done. And for those who had little faith in me earlier, I'm gonna show my chops. So g prime of x is the limit as h goes to 0 of, I've got x to the 3 halves, so I do x plus h to the 3 halves minus x to the 3 halves over h. So there are only 2 things you can do in math. You can multiply by 1 and you can add 0. And my professor Peter Jones at Yale said the log of 1 is, so there's really only one thing you can do in mathematics. So we multiply by 1. Does anybody want to give me a good choice of 1 here? Yes. Yeah. So let's take x plus h to the 3 halves plus x to the 3 halves over x plus h to the 3 halves plus x to the 3 halves. And then we'll get g prime of x is going to be the limit as h goes to 0, x plus h cubed minus x cubed over x plus h to the 3 halves plus x to the 3 halves times h. This part over here, we know how to handle. And this part over here goes to 2x to the 3 halves. So I will let you, put in the rest of the details. This works for an exponent of 1 half. What if I gave you 7/13 or 1781 over 24601? Could you do something similar in that case? Or is this very specific to 1/2? Or if you can do it in the more general case, is it going to just become a real pain? So the better way to handle this problem, again, this can be done, is to note, let's let a of x equal g of x squared. And what is g of x squared? X cubed.
Oh, yeah.
Right. Thus, a prime of x is 2g of x, g prime of x is 3x squared. And now solve for g prime. So the way we get the derivative of x to the 3/2, this would actually work for any rational power. That's much better than playing the game of multiplying by 1. But this is the technique that you should be aware of, and that's why I want to talk about this today. Multiplying by 1 is one of the most useful things you can do. It takes a lot of work to learn how to do nothing. And I'm happy to spend as much time as necessary teaching you nothing this semester. What about the last one? H prime of x is the square root of 2x to the root 2 minus 1. Can I do a similar trick there? I'm sorry? I can't just write, a of x is h of x to the root 2th power, because then I would have to still differentiate x to the root 2. Any thoughts on how we would take the derivative of h of x? Yes.
You take the log.
Rational approximations and then try and show that the difference between the actual and the rational is get.
So one thing is to take, a expansion of square root of 2, take more and more digits. Each one of them is going to be a rational, and try to prove that somehow this converges. That's one way to do it, yes. Was there a suggestion from Zoomerland?
Oh, I was suggesting that you take the log, but you need to know the derivative of the log first.
Okay, so that's actually the way to do it, is you introduce the exponential and the logarithm function. And then what you can do is you can say that h of x is x to the root 2. This is the same as as e to the root 2 natural log of x. And then use the chain rule. So need to know the exponential function and the logarithm function. So the point of this today was to try to show you how easy it is for math professors to slip things by you. Everybody, I think, knew that the rule, I give you x to the r, it's r x to the r minus 1. How many of you thought you had seen a proof of this before today? I mean, did they prove this to you in high school, or did they just basically say, Moses came down from Mount Sinai, and after he gave the commandments on how we should live, he went back up for more and brought back. And he also has that you need to take n equals 30 when you do stats and gather data. So did your teachers just say this is the derivative? Did they give you a proof, or did they really just do the proof of the case of an integer and basically just gloss over that this applies in general? It's very easy to accidentally give an argument that works in one case and think you have the result in general. And that's why I wanted to just spend some time looking at this problem today. Okay. How many people have ever experimentally discovered mathematics? Okay, if people are interested in doing so, we have lots of opportunities over the summer, and happy to talk to you about those. If you were the supreme creator of the universe, and you are choosing how the world will unfold and what the laws of mathematics would be, okay, and you now come to creation of calculus, what would you choose for the derivative of a product? Remember, you want to be worshipped by generations of calculus students. The derivative of a product is the product of the derivatives, and the quotient rule, the derivative of a quotient is the quotient of the derivatives, right? That's not what we have, right? We have a more involved formula. So you should have hopefully seen a proof of the product rule and the quotient rule, typically done by adding 0. I'm not going to prove the product and the quotient rule for you. I'm going to give give you an experimental way of seeing what it should be. Because again, going forward in life, you're going to be at the point where you're going to have to try to create new things. So I need a function whose derivative I can take, another function whose derivative I can take, and I want the product to be something I can take. So what's a good choice for f of x? X, a good choice for g of x. X squared, and then, great. So we could, of course, do things a little bit more generally. I could do f of x is x to the n, g of x is x to the m, and then h of x is f of x, g of x is x to the n plus m. So this will allow me to do many cases at once. 1 and 2 for the powers are great, but why not do a whole bunch all at once? All right, f prime of x is n x to the n minus 1, g prime of x is m x to the m minus 1, h prime of x is n plus m x to the n plus m minus 1, and I can write that as n x to the n plus m minus 1 plus m x to the n plus m minus 1. Does it make sense that the derivative of the product should involve f prime? Should f prime play some role in the derivative of f times g? Yeah. Why? Give me a good choice of g that will clearly show that f has to play a role. 1. And by symmetry, g prime has to play a role. We also know that f and g have to play a role. You know, if I take f of x to be 5 or 7 or any constant, I'm just rescaling things. So maybe I conjecture that f of x, g of x prime is a function of f, g, f prime, g prime. It seems reasonable that there might be something like this that works. Can you see any way to combine f, f prime, g, g prime to get h prime? So how can we combine things?
It's kind of spoiled by the fact that
Exactly. So what you can do is you can just do it by, since you know it now, you can answer it by using what you know. Did I tell you the story of how I passed my German test at Princeton? So I'm old enough that you had to demonstrate mathematical proficiency in 2 out of 3 languages, French, German, and Russian. And so I went to Gunning, and he just pulled a book off his shelf, opened it up, and told me to translate. And I noticed it was the rearrangement theorem, which I understand. And so I was honest and said, I know this is the rearrangement theorem. I can just recite the rearrangement theorem from memory, or if you want, we can see how bad my German is. So let's see how bad your German is. And so doing it honestly, I could not have done it, you know, if you just gave it to me individual words one at a time, but in context, I knew enough to put it together. So by all means, whenever you know something, feel free to use that. But when you look at this, we need to somehow get up to a power of x being n plus m minus 1. How can we get a power of n plus m minus 1? Well, the 2 different ways would be to have f combined with g prime and have f prime combined with g. And if you notice, when I multiply these together and add, it's going to equal that. And so we note that f prime of x, g of x, plus f of x, g prime of x equals f of x, g of x prime here. This is not a proof, but it gives us an idea of what should we try to prove. Now, are there any other functions we know where we can easily calculate the derivative of the product in terms of the individual pieces? One other one that you can do is, if you know some other things, for another example, f of x, bless you, is sine of x, g of x is cosine of x, and then h of x is f of x, g of x. What's sine x times cosine of x? Sine of 2x over 2. So it's 1/2 sine of 2x. So if you know some trig identities, you can actually use this as a second example to see that the product rule is true. Okay, so we talked last time about the definition of the complex derivative. So this is just stuff we've already done before. Basically, you just take the standard definition, and rather than writing x, you write z. Rather than writing the point A, you would write the point z naught. And the difference is h now can go to 0 along any path. And then you just show that all of the standard differentiation results hold, the proof is identical. And in complex analysis, we want to sound a little snooty, so we use holomorphic rather than differentiable. So holomorphic just means differentiable. So we get, if f and g are differentiable, so is their sum, so is the product. We have the quotient rule, we have the chain rule. And to some extent, we can now build up from this more complicated functions. If we take g to be a constant, then f times g would just be a constant multiple. So the proof is exactly the same as the proof from calculus and real analysis. There's nothing about those that required us to have real variable stuff. It's just as long as this limit exists, the same arguments give you all these rules. So we can try to build the derivative of complicated functions up from knowing the derivative of simpler functions. Okay. Let me just make sure that this is recording. I thought I could record. Yes, it is recording. Good. Okay. Okay. So you should have read enough of the book to know that we're going to be talking about the Cauchy-Riemann equations. Who would like to be the official keeper of Cauchy for the semester? Okay. Who would like to be the official keeper of Riemann for the semester? Okay. So your job is to keep track of how many times do we mention Cauchy or Riemann. And I will trust you. Hopefully you'll have similar rules as to what we do. So if I keep saying the Cauchy-Riemann equations, it only really should count as one occurrence of Cauchy. And the question is, whose name is going to be mentioned more often, Cauchy or Riemann? Later in the semester, Fourier might get into the fight. But in the beginning, it's going to be lopsided one way. So you should have seen the Cauchy-Riemann. If I give you a function of a complex variable f of z, I can write it as a real part plus an imaginary part. So I've got u of xy plus I v of xy. And it turns out that there are relations between the partial derivatives of u and v with respect to x and y in each other. So some notation. So du dx, we sometimes write that as u sub x. Du dy, we sometimes write that as u sub y. And so I believe that there is some relation between the partial derivatives of u and the partial derivatives of v if my complex function is complex differentiable. Okay. Now I can actually prove what they are. I can go through the argument in the book. But what I want to do is I want to experimentally discover what we should conjecture. I need a function which is complex differentiable. Can someone give me an example? Z. So let's start off with f of z equals z. This might be too simple of an example, but let's start with it. Can somebody give me another function that we can work with? Also complex differentiable. So we can't do complex conjugate of z. We proved that's not differentiable. Any polynomial, but it might get harder and harder. So what polynomial should we try next? Z squared. And then, of course, if you could do this for z to the n, that would be great. So we can write this as x plus iy. So u of xy equals x, v of xy equals y. Okay, what's du dx? Are people okay if I write u sub x, or do people prefer partial u, partial x? U sub x? All right, what's the derivative of u with respect to x? 1. What's the derivative of u with respect to y? What's the derivative of v with respect to x? What's the derivative of v with respect to y? So can you give me a conjectured relationship between the partials of u and v? It's okay if you're wrong. Just what would you conjecture from this? Yes.
One thing that you might incorrectly note is that y equals to that.
Yeah, so we've got 0 over 0. So Mark Twain has a tremendous number of wonderful quotes. One of my favorites is, "A cat that jumps on a lit stove will not jump on a lit stove again, nor will it jump on a cold one. To each experience in life, only draw from it what you should." And so we should not conclude that uy equals v of x, although that's reasonable to conclude from that. What would be a safer thing? The absolute values are the same. So we can definitely say it looks like ux equals vy, and maybe I should probably keep the same thing. Yeah, uy maybe equals plus or minus vx. This one's a little bit harder to tell. This is why it's good to look at z squared. So if we look at z squared, let's expand things out. So g of z is going to be x squared minus y squared plus 2i xy. If we just expand x plus iy squared. So here, u of xy is x squared minus y squared. V of xy is 2xy. So the derivative of u with respect to x is 2x. The derivative of u with respect to y is minus 2y. The derivative of v with respect to x is 2y. The derivative of v with respect to y is 2x. And so going back to our conjecturing, it still looks like the derivative of u with respect to x is the same as the derivative of v with respect to x. And if we look at the derivative of u with respect to y, it looks like it's negative the derivative of v with respect to x. So as a nice challenge, can you prove this works in general? So you'd have to maybe expand things out. You could also try to use these wonderful results we mentioned over here earlier. That we know things maybe for products, we can maybe build things up, maybe do some kind of induction. So as a challenge, it's see how far you can push this argument. Can you show the Cauchy-Riemann equations hold for functions of the form z to the n? Well, if the Cauchy-Riemann equations hold for a function f, and they hold for another function g, they hold for f plus g. Or more generally, they hold for af plus b times g. You should have seen this in linear algebra when you're trying to prove something is a subspace. You take your vectors v and w, and you show av plus bw is in the space whenever v and w are in the space. And so if we can show that it holds just for all powers of z, it's clearly going to still hold if we multiply all the z's by a constant. And then it's going to hold if we sum. The only thing that's a challenge is we don't necessarily know that every function is given by a series. And what if the series has infinitely many terms? Are we able to handle things like that? But for any finite polynomial, we should be able to prove the Cauchy-Riemann equations. Okay, any questions on what we're doing so far? So the Cauchy-Riemann equations are extremely important. The most common mistake is forgetting where the minus sign is. How can you remember the Cauchy-Riemann equations? Well, how can you remember something that will allow you to remember the Cauchy-Riemann equations? Could you do a matrix?
One thing that I've heard is that like the Jacobian resembles like a rotation.
Mm-hmm.
So it's like A, B, negative B, A.
Yes. But there's something simple you can do. It's on the board. Just take the derivative of z squared.
Oh, yeah.
Right? You know something, there's some relationship between the derivatives of u and v. Well, if I take z squared, this is a non-trivial example, and then that's going to tell me where the minus sign is. So as long as I know that there's something roughly of this shape, all I have to do is take the specific case of z squared, and I'll know which one it is. So this can be proven rigorously. So the Cauchy-Riemann equations. So the way we prove it is we look at two limits. Along x-axis, along y-axis. And so f prime of z is the limit as h goes to 0 of And this is where we have to be a little bit concerned about what notation am I using. When I write f of z, I'm really thinking of something as a function of a complex variable. And so I'll write it out very carefully as u of x plus h y plus iv of x plus h y minus u of xh plus v of x, oh, sorry, not xh, xy plus v of xy divided by h. So this is the limit as we come along the x-axis. And so when we look at this, we can group this as this is the limit as h goes to 0. We'll have u of x plus h y minus u of xy over h plus the limit as h goes to 0 of v of x plus h y minus v of x y over h. What does the first limit go to? Oh, yes, I dropped the I over here. Thank you. And then there should be an I over here. Thank you. Do you know what they say about complex analysis? It is only fun until someone loses an I. So thank you. Yes, that is very important to keep. What does the first piece go to? Just u sub x at xy plus I times v of xy. Yep. And so now we have, this is f prime of z. We calculated f prime of z by taking the limit along the x-axis. Because the function is differentiable, the limit exists no matter what path we take. So if we take any other path, we have to get the same answer. So now, compute f prime of z going down the y-axis. And that will give you f prime of z. And what do you think it's going to be when you do the analysis? Well, let's see. We're conjecturing that the Cauchy-Riemann equations is u sub x equals v sub y. So this should be u sub y of xy minus I v sub x, I think, of xy.
Yeah.
Oh, sorry, this should be v sub x. Thank you. Yes. Should be v sub y over here. Which makes sense because we're taking the derivatives along the y-axis. So you have to check this. So I will leave that calculation for you to do. But knowing what the answer is going to be, when you do the calculation, you'll see this. And it's a very similar calculation. Instead of coming along the x-axis, we come along the y-axis. This is a good way to just practice what you're doing. For the most part, if your functions are nice, you only have to worry about coming along the x-axis or the y-axis. There are some functions which are not nice, and real analysis is heavily populated with them. So the way I like to phrase it, and this may not be politically correct, is real analysis is a very democratic subject. All functions are welcome. Complex analysis is the exclusive country club which has been sued multiple times for policies that discriminate against large segments of our population. Complex analysis only allows a very small set of functions to enter and be considered differentiable. It is not a big deal to be real differentiable. This is the participation award that you get from showing up. I've been assured, though, that what I got for doing the 10K yesterday was not a participation award, that I had a legitimate time from people who actually run. Complex analysis does not believe in that. It is a huge deal to be complex differentiable. And so almost all of the pathological counterexamples that you have in real analysis do not happen in complex analysis. Yes?
Yeah, could I ask why, like, the second derivative like is UYXY minus IVYXY instead of V.
Oh, sorry. Yes, sorry. It should be V. Sorry. These were flipped. Yes. Yes. Okay. This is unfortunate. Sorry. It should be, yes, it should be V here and the U here. Yes. And so I strongly urge you just go through and do the calculation. So in complex analysis, it is a tremendous difference to be complex differentiable than being differentiable in real. It implies so much more information than you have otherwise. And so I'll just jump to, so it's at least being recorded. So here is, the nice statement of the Cauchy-Riemann. It's not displaying. Oh, there's just a very long lag. Okay. So, the Cauchy-Riemann equations, du dx equals dv dy, and du dy equals negative dv dx. These are extremely important. So after you do the multivariable calculus test that you have, if you haven't seen Green's theorem in your life, you should watch the lecture on Green's theorem. We're not going to be using Green's theorem directly in what we're doing this semester, but the ideas behind the proof of Green's theorem are essentially how we're going to prove results in complex analysis. The whole point is to evaluate certain integrals. And it turns out that you can convert a lot of very difficult integrals to simple ones. And so we don't have that much time left today, so I will just say very briefly, this is where it's nice that the green button is easy, Green's theorem. You should have something like, oops, I have some curve, gamma, and the integral over gamma of do it this way, of p dx plus q dy is the double integral over the region of dq dx minus dp dy dx dy. And what you should really be doing is you should be viewing f of x as p of xy, q of xy. And so when we're thinking of things of a complex variable, you should be thinking of this as u of xy, comma, v of xy, or u plus iv. And so we'll talk more about this later, but the idea is we can convert certain integrals along a boundary to integrals over a region. What would be wonderful for that to equal? If you could choose anything in the world for that to equal, what would you choose? 0. And the Cauchy-Riemann equations tell you if your function is differentiable, that's 0. And that's why so many integrals become nice in complex analysis, because we restrict ourselves to nice functions to integrate. And then it turns out you can approximate a lot of things with this. All right, so this is a good place to stop.